on, and we're going to talk about this Mathematica stuff that I have over here in a moment. Okay, so here is an example of our first mechanism. So the balanced equation for the reaction of gaseous nitrogen dioxide and fluorine is the following. So this is like our overall reaction. And this is what we would often be used to seeing. Two NOs reacts with an F2, it makes 2NO2F. We can see that it's all balanced. And if we were to look at this upon first inspection, we might guess that it's third order because we have two NO2s and one F2, right? 2 plus 1 gives me 3. But we don't know that because this is the overall reaction. We need to look at a mechanism, which is several steps, and we need to look at the reaction order of each of those steps, okay? So a suggested mechanism, and this is really important, this key word here, suggested, because once again, it's all theoretical. It's not like we can shrink ourselves down to the size of atoms and molecules and actually look at all the individual steps taking place. We can do this experimentally with great challenge, and we can also do this theoretically by examining the molecular structures, the Lewis structures, for example, and using our periodic trends and our knowledge of chemistry to kind of guess which step might be slow and which step might be fast. And so here's how we could do that, okay? So if we were to look at the Lewis structures of these things, and so for example, the Lewis structure of NO, I'm just going to put that together really quickly. NO is a radical, so it's got one unpaired electron. And it also has a resonance structure, but I'm not going to be too worried about going through that resonance structure. I just want to get one of the Lewis structures drawn. Okay, and so now we can see that the other reactant is an F2. And now this is very much going to be a Lewis acid, Lewis base situation going on where we've got some molecules that are electron rich and some molecules that are electron poor. And so you can see that's our nitrogen right here. Okay, so as it turns out, that one single unpaired electron really wants to get paired up. And so the way that those react, one electron pair joins with this electron pair. This is called the fishhook mechanism, where we actually like draw a fishhook. So that electron pair and that electron pair make a chemical bond. But now what we've done is created Texas fluorine. We've got too many electrons on fluorine. So now what that means is there's two electrons in this bond. One of them gets kicked out to that fluorine, and the other gets kicked out to this fluorine. And what we're left with is ONO. We keep our double bond there. We keep our single bond there. And now we've made a new bond with fluorine, right? And then if you notice here, what we're left with is one single fluorine. And if we count our electrons, we had 2, 4, 6 on this side. Well, now one of those electrons went to this fluorine, the other went to this fluorine, and so now we end up with a fluorine, another fluorine radical with 7 electrons. This fluorine had 7 electrons, but the nitrogen added an 8th electron. Okay, so that's just the first step. So now we have to see what happens in the second step. And what we notice here, our F atom is an intermediate. Okay, so let's go back to that. A species produced in one step of reaction and consumed in a subsequent step. So F atoms will not survive for very long. So as soon as we produce an F atom, it's going to react quickly. Because an F atom, right, halogen, it has one unpaired electron. It really wants to pair up that electron. So now we have another NO2, okay? And we'll get the Lewis structure of that NO2. So it's the same Lewis structure here. We've now created another radical with an unpaired electron. And now these can do another fishhook mechanism. And then finally, that's going to make a second NO2F molecule and all of our unstable reactants, which would be the F atom, have been reacted away. Okay? And if we were to balance this thing, so I'm going to draw a line under here and say plus. So if we were to add these two reactions together, we could see the F and the F cancel. And what I end up with is two NO2s plus one F2. And that makes two NO2F. And that's consistent with my overall reaction. So now you notice that I've got these things that say slow and fast. And how did we know they were slow and fast? Well, we have to use our chemical intuition. Okay? So now let's break this down. So in this first step, a chemical bond has to be broken and a new chemical bond has to be formed. That's going to take time. Okay? So F2 is stable. Right? And furthermore, we recognize for this reaction to go, it is going to have to collide in a specific way, right? That F is going to have to find the nitrogen and collide in that orientation. That's just going to take time. That might not be obvious right away for you all as beginning chemists, that this is going to be slow, and that's okay. That's why I mentioned earlier, it's really difficult to do this theoretically. But that's why if we write out this Lewis structure and we start imagining all the steps that have to happen, we can see here a bond has to be broken and a new bond has to be formed. And we make this unstable intermediate that is going to react very quickly. We know it's going to react very quickly because it's got an unpaired electron and it's reacting with another thing with an unpaired electrons. So two species with unpaired electrons are going to react immediately upon collision to make that final bond. So what that means is if I were to number these as step number 1 and step number 2, we would say step number 1 is rate determining. That's the rate determining step. So in other words, it doesn't matter how fast your car can drive. If you get stuck behind traffic, that's as fast as you can go. So this second step, it does not matter how fast it is. What is limiting this reaction, the rate limiting step, is the slow step. And so now, because we know these are elementary steps, we can say definitively, this is a bimolecular reaction because there's one NO2 and one F2. And this bottom one is also a bimolecular reaction because it has one NO2 and one F atom. But what that means, because this is rate determining, that means our rate law for the total observed reaction is going to be rate equals K times NO2 to the first power times F2 to the first power. That's my rate law. It is second order overall, first order in NO2, first order in F2. Even though the main balanced reaction, we might have guessed third order because it's showing there's two NO2s and one F2. But we recognize now, hopefully we do at least, that when we break this reaction down into its simplest steps, the rate determining step is a second order step, a bimolecular, same as second order. And it doesn't matter how fast this step is, this first step is rate determining.